Okay, so the story starts with in this case, a regular tetrahedron without loss of generality, and some point P chosen in its interior. G actually represents the centroid of this tetrahedron. And GP is the isogonal conjugate of P with respect to this tetrahedron. In this case, P is interior to the tetrahedron, but it's without loss of generality. I'm just drawing a line that connects them two here for purposes that are going to become clear. I can, of course, change P and get another GP. I'm going to keep this sample P fixed here so I can show the following surface. Okay, so there is a constraint surface, a two-dimensional constraint surface, okay, of translations of the whole tetrahedron, rigid translations. You can see that the surface here is an XYZ space, okay, of translations. Its geometry is not going to be explained here, but it's a two-dimensional self-intersected surface in XYZ space, okay? And for every point on this XYZ surface, there are two rotations about x and y by theta and phi, such that the isogonal conjugate of the transformed tetrahedron is preserved. Okay, now let's visualize what I mean by that. Let's, for example, draw a transformed tetrahedron, which is going to be shown green. Okay, and right now I'm transforming it by, if you use this transformation, this rigid transformation matrix product here, I'm going to transform it by nothing, by the identity. Theta is 0, the rotation about x. Phi, the rotation about y is 0. And I'm not including a rotation about z, so I get only 5 degrees of freedom. And then I have a translation of x, y, z. So I'm getting everybody at 0 here. So of course, if I don't translate the original tetrahedron, the isogonal conjugate of P with respect to this default reference tetrahedron is going to put me right on GP. But what's interesting is, for example, I can vary theta, if it's going to allow me to do that. I can vary, sorry, here I'm varying phi. Okay, theta is being kept at 0, so the rotation about x is being kept at 0. But I'm varying phi, okay? And as you can tell here, let me go ahead and get rid of the surface. There is a variation of the center of mass, showing here as G prime, okay, or the centroid, along what looks like a planar ellipse, okay, such that the isogonal conjugate is left undisturbed. So you can see here there's motion in 3 dimensions. Along just, you can see I'm only varying phi, the rotation about y, okay, and everything is getting preserved. What if I want to rotate about theta? Now for phi held at 0, this is kind of a pleasant observation. There is a linear motion of G prime accompanied by a rotation of theta about the x-axis of the original tetrahedron that preserves GP. Of course, I can vary both at the same time, right? And I'm going to fall at a point on this surface. If I vary both, if I'm allowed to choose a particular theta and phi, I'll fall anywhere on this two-dimensional surface here, which, it has kind of like a, let me go ahead and turn off the display of the translated and rotated tetrahedron and just focus on the surface. One name for the surface, you can see that it's self-intersected. One name, you can see that the G of the original tetrahedron lies at what seems like a crease or some sort of singularity of the surface. There's this crease up here as well in XYZ space, or a rim, right? Which is kind of interesting. And this surface, it has kind of like a mirror underside to it, okay? It has a mirror underside to it, it has a mirror rim, right? You can see here the surface seen from, let's see here if I can do this, from its profile. One interesting question is, and I know I've been arbitrary at keeping the transformation in 5D so I can get a surface. But what is the genus of this, and what if I allow for the full 6-dimensional stuff to take place? So for example, when I go back to my triangle and I'm at the 0 phi, or the 0 rotation about y, as I pick a different theta, okay, let's see if I can do this. Yes, so let's move out. Let's move out like that. If I pick a different theta, the center of mass G prime, and let me get rid of the surface so this animation is faster. My center of mass G prime is simply moving along a straight line. That's an interesting result in itself, right? While preserving the isogonal conjugate. Anyway, if I pick a different slice, okay, for example, and what do I call slice? This is a different, in this case, phi slice. Okay, so if I keep my phi rotation about y constant at 20 degrees, my center of mass G prime, or my ensemble of translations, I have found observationally that it's going to move along a planar ellipse in 3 space. However, if I pick constant theta at 20 degrees, the curve that the center of mass of my rigidly moved green tetrahedron will display is a bit more complicated, right? It's a space curve, it's not planar. You can see here that, let's zoom in, that space curve is not planar. As I vary my phi, I get this non-planar space curve. That is on the surface. If I bring the surface back, of course, this is going to lie on that constraint surface that I talked about. Okay, so that's what I have for this video. See you on the next one.